So hypothetically, we have a site where there is a leaky waste oil tank. And if you've been in site cleanup, it's like one of the worst things you can come across because there could be anything in a waste oil tank. So in this case, we've sampled the groundwater below the tank, and we've found elevated levels of zinc, the solvent TCE, benzene, and xylene. Our goal is to find out, has pollution occurred? If we can document that pollution has occurred, we can take enforcement. So the very first thing I'm going to do, look at the basin plan. What are the beneficial uses of that groundwater? What are the water quality objectives that apply to protect those uses? Then we're going to start running through the algorithm and select numeric thresholds for each objective. Which of those is most restrictive? Compare that with concentrations we measured in the groundwater, and that will tell us whether pollution has occurred or not. If measured concentrations are above the assessment threshold, you have a violation of one or more water quality objectives, and you have essentially shown there has been pollution from that activity, which allows you to adopt a cleanup order or a cease and desist order or a lot of other things. Okay, so let's look at the groundwater algorithm for these constituents of concern. First of all, the chemical constituents objective. Look at your basin plan. Are there numeric water quality objectives? Second, MCLs. We're going to assume this water body is a source of municipal or domestic supply. It's listed as MUN in the basin plan. So our primary and secondary drinking water MCLs would apply at a minimum. And here they are for those 4 constituents. Agricultural use. Zinc has an agricultural use limitation of 2,000. It's lower than the secondary drinking water MCL. There actually is a draft federal MCL for xylene, a secondary MCL, that is lower at 20. But it was never finalized. Don't use it. So of those numbers, these are the ones we're going to write down, including what we found in our basin plan as a numeric objective. All right, let's look next at the toxicity objective. So for human health, drinking water exposure, we find in the database 2 different thresholds, one from EPA's Integrated Risk Information System as a reference dose, and also an EPA health advisory marked draft. So first of all, because the health advisory is marked draft, we're likely not going to want to use that because it wasn't finalized. Realize in this case, though, it's actually just rounded off to 1 significant figure from the reference dose in IRIS. We're going to use the IRIS number. Those are updated much more regularly than health advisories, and it's not a draft value. Gets a little more complicated for trichloroethylene. So in this case, human health drinking water exposure, we have a lot of different numbers in the database. So remember, we have a hierarchy of criteria based on preference for California values, values that reflect multiple exposure routes, all linking to use of water in the home, and also the fact that they're renewed regularly, so they're up to date. Public health goals satisfy all of those. Notice the difference between the public health goal and the cancer potency factor. Those essentially are both 1 in a million cancer risk levels. Why are they different? Remember? TCE is volatile. It's a volatile organic contaminant. Public health goals consider multiple exposure pathways relating to use of water in the home. Drinking the water, breathing the vapor that resulted from running water in the house, and exposure through the skin while bathing. So the calculation of a 1 in a million cancer risk level is going to wind up with a lower value when you're considering all of those exposure routes, as opposed to the cancer potency factor, which only looks at drinking water, 2 liters a day. Okay. We also have numbers in IRIS. The reference dose is for your threshold toxicity, then the cancer risk estimate. Notice EPA has a lower number than OEHA does. There's a health advisory for cancer risk. There's an MCL goal of 0. MCL goals are always 0 for carcinogens from EPA, because any amount is theoretically linked to some risk of cancer, and that's the way they interpret their statute. And then we have an NAS value that's fairly old and a Prop 65 no significant risk level that is fairly high. So of these values running through the algorithm, we've got a public health goal. That's what we're going to use. So California agency has developed it. It's renewed regularly, so it's up to date. And it has more relevant exposure pathways to the use of water in the home than other numbers we have in this table. Those are the kind of rationales that you would put in your findings of your order. I want to use the public health goal. Here's why. Benzene, similar situation. We've got a public health goal, cancer potency factor. You know now why they're different. IRIS values, health advisories, MCL goal again of 0, carcinogen, and Prop 65, cancer risk and reprotox values. And again, public health goals, sister California agency, consider more exposure pathways. It's a volatile organic and are regularly updated. Xylene. In this case, I included the MCL because the MCL hasn't been adjusted for technologic or economic constraints. Notice it's the same as the public health goal, just 3 significant figures rather than 2. Okay. So we'll write down both the MCL and the public health goal. So here's a summary of the toxicity values from running down the algorithm for these 4 constituents. Taste and odor. So we have a secondary MCL for zinc. We also have a federal secondary MCL. It's the same. I mentioned there was a draft secondary MCL for xylene that EPA published a while back in a Federal Register, but they never finalized it. Don't use it. The EPA National Recommended Water Quality Criteria published the taste and odor value and organoleptic threshold for zinc of 5,000, same as the MCL, secondary MCL. And then in a 1989 Federal Register and US EPA drinking water fact sheets, they published peer-reviewed literature values for taste and odor thresholds for xylene at 17. There's also peer-reviewed journal articles that cite odor thresholds in water for benzene and TCE. These are the numbers that we're going to use based on the algorithm. So here is a summary of what we have for numeric thresholds for zinc. You're going to look in your basin plan and see if there's a numeric objective. You can look at the MCL, the ag use value, the toxicity value, the taste and odor value. These all will be in your little table that you've created using the groundwater algorithm. And of those, the assessment threshold is the most limiting of those. So it would be 2,000, the ag limit, unless you had a numeric objective that was lower in your basin plan. Question?
So if a drinking water standard is higher than the Office of OEHA, the health hazard, so the regional, let's say, makes a basin plan with a more stringent discharge parameter on our threshold objective on the, let's say, like TCE, for instance, the 1.7 you just gave an example of. I believe DDW, I want to say it was like 7, similar to the one that was from the Toxicity.
So remember, the MCL and the public health goal are different. They do different things. Public health goal is a purely toxicity-based number.
Okay.
The MCL can consider other things. So for example, one of the things that the Division of Drinking Water has found in looking at TCE all around the state, there's a lot of polluted groundwater that's source water to a number of municipal drinking water supplies. and there would be a cost associated with removing the TCE in supplying that drinking water to customers. So they've decided for cost purposes to accept a certain amount of cancer risk. They're required to review that every 5 years and change the MCL to be as close to the public health goal as is feasible at the time. So that's the difference. All right. All right, so here it is for TCE. We have a basin plan number if there is one, the MCL of 5. We have no other beneficial use protective criteria, toxicity number, taste and odor number. So in selecting our assessment threshold, it's going to be the toxicity value that wins out. Same thing for benzene. Toxicity is going to be the most limiting factor, and that will drive your assessment threshold selection. For xylene, it's a little different. Taste and odor. Taste and odor is what limits the beneficial use first, much below toxicity by 2 orders of magnitude. So here's a summary of the assessment thresholds that would come out of running the algorithm for groundwater on these 4 constituents. So you would look at these numbers and compare them with what you measured in groundwater. If what you measured in groundwater is higher, you have evidence that pollution has occurred. You, of course, need to write down all the rationale in the findings of your cleanup and abatement order that you'd bring to the regional board to get that problem corrected. Okay, what if you're analyzing for something and you get a result back from the lab where their quantitation limit is too high? Your assessment threshold is below what the lab said it could quantify at the time. So you get an ND result, but let's say their ND result, their threshold for saying ND was 10 times your assessment threshold. What do you do? I'm going to keep running because we've only got like 17 minutes before 3 o'clock hits, and I'll take your question at the end. Thank you. So there are a number of places where you can look for how well the lab should do in analyzing your samples. There may be some constraints, but there are some good places to check. Is there another analytical method the lab could run at a reasonable cost? So one place to look is the minimum levels in the appendix of the state implementation plan for the CTR, because it lists quantitation levels that labs ought to be able to meet in determining compliance with CTR criteria. So that'd be a good place to look for, is there a method that has lower quantitation limits that I can reasonably require be run? Ocean plan, same thing. There's a minimum levels appendix that provides quantitation limits that labs ought to be able to meet. The drinking water program also has an exhaustive list of what they call DLRs, detection limits for purposes of reporting. They're quantitation limits for laboratory work that's being done on drinking water sources and also at the tap. See how well they figure labs ought to be able to do. Sometimes you have to go back to the original methods. A lot of these analytical methods are available through a website called the National Environmental Methods Index, NEMI. NEMI.org is where you'll find them. And the original documents for the different methods tell you what's the performance of this method. How low should it be able to quantify a concentration of a substance in the sample? Now, there are always some situations where there might be certain other things in the sample that interfere. Those method documents will tell you. It's like, for example, sometimes a high sulfate result will prevent you from getting low enough for some other constituent in analytical work. But the lab should tell you that. The laboratory report coming back should say, couldn't meet this because had this problem. All right? If they're unable to, ask them to do better. What if you have multiple chemicals together in water? I mentioned the concept of additivity before. So in the policy for application of water quality objectives that the Central Valley adopted, We borrowed language from regulations adopted by the State Water Board in the landfill program. In the landfill program, if you have a release from a landfill and you're trying to figure out what should be the cleanup levels in groundwater if you can't reach background, one of the requirements is to consider additivity of toxic effects. And it says when there are multiple toxic pollutants together in water, there's a potential for toxicologic interaction. Generally, we will assume additivity for all carcinogens, and then separately assume additivity for all pollutants that manifest their toxic effects on the same organ systems or through similar mechanisms. So the Regional Water Board just borrowed that language from another regulation and popped it in the basin plan, and that's how it's used. Here's the formula for which you use to determine if I have an additive toxicity problem. What you're doing is you're taking the concentration you found divided by its toxicologic threshold, whether it be a reference dose or a cancer risk threshold or public health goal. So you're normalizing the concentration by how potent the toxic effect might be from that chemical. And then you're going to sum those ratios up for all the constituents that you're together are assuming to be additive. So at least for all carcinogens. If the sum is less than 1, no additive toxicity problem. If you're equal to or greater than 1, you got a problem. So let's look at our example of the waste oil tank and groundwater impact. There were 2 chemicals in that example that were carcinogens, benzene and TCE. Here are the concentrations that we found in groundwater. Here are the 1 in a million cancer risk estimates as published by OEHA. We run the calculations, we have 1.5 cancer risk per million people exposed over a lifetime, according to the language in that regulation for the landfill program or in the Central Valley Region Basin Plan. That would be a violation. All right, the last thing I wanted to cover in the last few minutes of the class is anti-degradation. So why do we have an anti-degradation policy in the first place? Well, if you think about water moving through the environment, let's say snow falls in the Sierras and melts and gets into a creek, and some little vacation cabin has an intake from that creek, and that's where they get their water supply. And then they have a pit toilet out back, so that's where their wastewater goes, and it percolates into the subsurface, and eventually it might pop back into the same creek a little further downstream and moves down. Let's say it gets to a small town like Placerville. Placerville has a drinking water intake for their system. They serve that water to their customers. It eventually winds up in the toilets. It eventually winds up at the sewage treatment plant, and the effluent from that treatment plant goes back into the same creek a little further downstream. And then it comes to Sacramento, and the same thing happens, and it flows into the delta, on and on and on, all the way to the ocean. Every time the water is used beneficially, it's also degraded. It's almost impossible to use water beneficially without degrading its quality. And there are also many other human activities besides water use that can degrade water. Spills, chemical accidents, those kinds of things. If we were to allow a single activity or use to degrade the water quality to just below the water quality objective, there's no room for the degradation that's going to occur by the next use downstream, down gradient. We're going to have a problem eventually. That's one of the reasons why we need to have water better quality than our water quality objectives. The other reason, we just don't understand the potential health and environmental effects of all chemicals on all uses. What we have is a small fraction of that understanding. And every time we get more information, there's a chance that our estimates are going to get more stringent. As I mentioned with cadmium and the difference between EPA's California Toxics Rule criterion for aquatic life protection and the EPA recommended water quality criteria that are newer. We now know cadmium is much more harmful to aquatic life than we knew back in the year 2000. So what's safe at 10 ppb today may be found harmful at 1 ppb tomorrow. So it's desirable, again, to keep our waters in better shape than designated in our water quality objectives. So for that reason, we have an anti-degradation policy. EPA requires all states and tribes that have promulgated or delegated authority under the Clean Water Act to have an anti-degradation policy. Ours was actually adopted a long time ago, 1968. And it says whenever the existing quality of water is better than the quality established in policies, in other words, it's better than our water quality objectives, such existing high quality will be maintained until it's been demonstrated to the state that a number of factors are met. First of all, that the change in water quality is consistent with maximum benefit to the people of the state. It will not unreasonably affect present and anticipated beneficial uses of such water, and will not result in water less than prescribed in state policies, such as the source of drinking water policy. Goes on to say that any activity that produces or may produce a waste which discharges or proposes to discharge to existing high-quality waters, waters that are better than our water quality objectives, those will be required to meet waste discharge requirements, which will result in best practicable treatment or control of the discharge necessary to ensure that pollution or nuisance will not occur, and the highest water quality consistent with maximum benefit to the people of the state will be maintained. So we're right back to this figure again. Within the gap from natural background at the most stringent to our water quality standards as the least stringent, including all of these different requirements, there is a range of water quality that's appropriate for us to maintain. Within that range, there are factors pushing in opposite directions. Economics, jobs, housing, it's going to push things towards those water quality standards because it's cheaper to do that. The concept of anti-degradation pushes the other way. How many times is that water going to need to be used? What are all the factors that could affect the quality of water based on that constituent getting into the water? So again, this is why we have boards to make the ultimate decision. Where within that range do I set the receiving water limit? They need to consider all these different factors. So an anti-degradation analysis is also one of the things that needs to be required, not just are we in compliance with standards. Okay? Because if we go above the standards, we have pollution, and that's illegal in California. Yes?
I was going to just ask more along the lines, if you
Quick,
have pollution,
yeah.
what happens with contamination? What do you guys do? Are you guys hitting with fines, a regional water board? Or
Okay, so the question is, what do we do? What do we do if there's a violation of water quality standards? The board has a number of tools that it can use. It can first cajole people into complying. And if that doesn't work, there are a number of regulatory tools that can come. Enforcement orders, so a cleanup and abatement order to clean up the problem and abate the effects of the problem. There can be a cease and desist order, shut down your operation now. And you can't continue doing business until you come back into compliance. We can fine people, administrative civil liability. We can say, okay, you've done this according to factors that are in our regulations. We can slap a fine of so much per day or so much per gallon of discharge that was in violation. We can refer cases to the Attorney General for prosecution in court. So let's say we're dealing with a multinational corporation that might be a little difficult for our individual regional water board to go up against. Refer it to the AG's office, let them fight it for us, supply them, of course, with all the rationale. There's a lot of things that we can do. Okay, you also had a question earlier. There's time for it now.
No, I'm sorry. I thought you were asking a question and that question was online.
Okay, very good, very good. Any other questions? You're saturated. Thanks for your time today.
What about going the other way? If you have a water body that's exceeding water quality objectives and you bring it back down, you just bring it back down to the standard?
It's not technically covered by Anti-Degradation policy. It's not high quality water.
Right.
That's correct.
I'm saying where
That's a good point. So
It's only bringing down
the point
to-
was, first of all, the question was, when you're trying to correct a pollution problem, how far do you go, or are you only bound by the water quality standards? And the answer, one of the answers, was that you're only bound by the anti-degradation policy if you're starting out with high quality water. High quality water is the waters that are better than our water quality objectives, and you're trying to determine how much degradation is allowable. Right. So mostly in a cleanup scenario, you're looking at eventually coming into compliance with water quality standards. And that's pretty much it. Okay? And in some cases, we can't even get there. It's pretty hard to bring groundwater that's been polluted by organic solvents back into compliance, even with just the MCL. You know, you'd be pumping for decades and still maybe not get there. It's pretty hard to do. But we try. Sometimes we put long time schedules on things. Sometimes we just give up, and that's unfortunate, I think. Other questions? All right, you should have in front of you an evaluation form. If you don't, I put some along the center row. Grab one, please fill it out. When you're done, please leave it on the table where the sign-up sheets are. And if you have not signed in for the class, make sure that you do that. You won't get credit for the class unless you've signed in. Okay. Thank you.